Okay, let's get started here. I'm on the wrong day. Lava Island Hiking Guide. Scorched by Lava. Topographic map, which is our inputs. Okay, so we have to fill in the missing hiking trails that have been scorched by lava. Topographic is height and shape. Indicates the height at each position using a scale. Okay, from 0 to 9. So these are different heights of a island. You determine that a good hiking trail is as long as possible and has an even gradual uphill slope. Okay, for all practical purposes, this means that a hiking trail is any path that starts at height 0, ends at height 9, and always increases by a height of exactly 1 at each step. Never diagonal. Okay, so this looks like we're going to have to maybe like breadth first search from the 0 and always check all 4 cardinal positions if the step above us exists, and then if you get to 9 then the trail exists. We also have to have like a visited array probably, so we don't like go back and forth from like, well actually we might not need that because 0 to 1 is, you can go 0 to 1 but you can't go 1 to 0. Okay. Reindeer, small piles of pencil, markers, rulers, compasses, stickers. A trailhead is any position that starts one or more hiking trails. Always have height 0, that makes sense. More fragments of pages, you establish a trailhead. Score is the number of 9 height positions reachable. So this is like once we find all of the reachable positions, we use the score probably as the final answer, right? Yeah, okay. So a score is the number of 9 height positions reachable from that trailhead. Okay, so a trail can have several like summits, which are the 9s. In the above example, the single trailhead in the top left corner has a score of 1. So yeah, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You could also go this way. But since there's only one peak, then its score is 1 because it's the number of 9 head positions reachable. So it doesn't matter how many different ways you can get there. This one has 2 because there's 2 paths. Okay. Are impassable tiles? They do not appear on your actual map. This trailhead has a score of 4 because every 9 is reachable via a hiking trail except the one immediately left of the... Okay, so that's unreachable. 1, 2, 3, 4, 5, 6, 7, 8, 9. So can a map have several trailheads? Yeah. Okay. So I think what we want to do is like... Alright, let me keep reading. But either way, I think what we should do is like the same algorithm for every trailhead. Okay, 9 trailheads, which is zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. All the trailheads in reading order. They have score of 5. So this one can reach 5 9s. This one can reach 6 9s. This one can reach 5 9s, and so forth. And this one can reach 5 and 36. Okay. So yeah, it looks like you kind of almost want to, like if you imagine every point as a node connected to its north, south, east, and west nodes, then you kind of want to breadth first search from every 0. I mean, I guess it doesn't have to be breadth first search actually. Yeah. Yeah, I just did a problem like this. It was like a water flow problem, and that one you actually did have to BFS, but I think this one, it doesn't matter which order you... Yeah, it doesn't really matter which order you do it. Maybe DFS actually makes more sense, because then you'll find the 9 right away. Because you could have something like... that's a 3. Which I think was like in this example, yeah. So here at this 0, you would check for any 1s in any position. You find a 1, do the same thing but with 2s, do the same thing but with 3s, and then you do the same thing with 4s. And with DFS, you could just keep going all the way until you get the 9, and then you'll go back to the recursion stack where this 4 existed. And then just keep doing that. And then that would be for that 0, and then you repeat the process for every 0. Okay, and back to the visited array thing. So it's impossible to go in cycles with this code, because you must always go in ascending order, so you can never go backwards. So we don't have to worry about that. So yeah, you can never go backwards. Okay, so I think we want to start by just writing it for one trailhead, and then we can just loop through the trailheads. So we want a function. So we want one function which will be like solve trailhead, which takes in the grid, and then it will return score. So for every trailhead, it will return the score. Yeah. I'm thinking we could maybe use recursion. So we could have a function called like check adjacent, and then if like the one, so it checks for all 4, and then if any of those 4 are what you're looking for, it will check adjacent on that one. We could also maybe just use a stack. Okay. So I kind of like to break up problems a little bit, so let me think more about what exactly is going on. So we start with a 0. So let me just pick a example here. I guess it's too hard. This one. Okay. So 0, 1, 2. This red is a little difficult to read. 0, 1, 2, 3, 1, 2, 3, 4. I think it was like 5, 6, 7, 8, 9, 8, 7, 6. Okay, so we start at the 0, and then so we'll check like each direction. So if like up, if the tile above us is like my value plus 1, then we want to search that tile. So it's like search up. And you do that for all the directions. So if you search this one, you want to do the same thing. And then we'll get 2, and then 2 will check for all the 3s. Okay. So this would help you, I think, with how many paths there are. But we don't really want that, because like we would get that, and we'd also get this. So we just want to know from 9. So I wonder if it makes more sense to just start. I was going to say start from the 9, but you get the same problem. So maybe what we could do is like calculate every possible path, and then just say, you know, when we encounter a 9, check if we've already had visited that 9 before. So we could say like summits visited, and it'll be a list of tuples, which are positions of the 9. So this would be row 3, column 0. So then whenever we reach a 9, we check if it's in summits visited. So like for instance, let's say our DFS goes like that. Then once we reach this 9, we add it to summits visited. And then when we go back the recursive stack to this one, and we reach it again, then we obviously wouldn't add it twice. I'm wondering though, here we're repeating like a lot of trail, so I'm wondering if every time we visit something we should just make it impassable. But will there ever be a time where we have to, yeah, so we can't do that because for instance, this example, if we made everything impassable, then we would never, yeah, like so if we went this way and then there ended up being like a 7 here, well, I guess maybe it's fine because you would just go to this 6 and then explore that 7 right away. What if there's a 9 here? Yeah, this seems like kind of simple. And let me see the puzzle input. Like maybe it's not that big. Okay. So I think I'll just do it this way for now. It might save you time if you just don't visit things that are already visited. It might be worth figuring that out now, actually, before I start coding. Okay, so all right, so let's trace it here. So if we start at 0, we're gonna check all 1s. So now this one and this one. Okay, and now from every 1, we're gonna check all adjacent. So let's say we search this one first. Actually, yeah. So if it was like up, let's say if we do clockwise, it would be up, right, down, left. Okay, so we check up, that's not in bounds. Then we check right. Okay, and now we instantly go to this one and do the same thing. So we check up, that's not in bounds. We check right. Up's not in bounds. We check right. Up's not in bounds. Right's not in bounds. We check down. Up does not fit the criteria because it is not my value plus 1. We check right, that's out of bounds. D is good, so we go here. Up doesn't meet the criteria, right's out of bounds. D is good. Up doesn't fit the criteria, right's out of bounds. Down is out of bounds, left is good. Up doesn't work, right doesn't work. Down doesn't work, left works. Up doesn't work, right doesn't work. Down is out of bounds, left works. We've reached a 9. So I guess I'll just say 3, 0. Okay, so then we would go back. So if it's 9, that would be like your base case. Yeah, if it's 9, you just stop. So then we go back to the recursive stack. So with 8, we checked all of them, so that 8's done. 7, we checked all of them, so 7's done. 6, we checked all of them, so 6 is done. 5, so that was all in the down call of 5. So left, so now we go left. Left is good. Okay, so now this is the interesting part right here, in this 6. So we just searched this 6. So it's going to check up. It's going to check right. It's going to check down, and down is good. Okay, so this relationship here is interesting. So down is good, but we've already visited it before. So I think since we've already visited this node before, it makes no sense for us to visit it again, because we would have already found all possible 9s from this. So I think we can actually not visit. We don't have to visit things twice. There's no path that like only runs this way that we wouldn't have found through. Even if a 0's here. Wait, what if a 0's there? So if we have 5, 6, 7, 6, and let's just say this path like goes to 0. Well, if you're at this 7 and it's valid, it means it comes from a 0 anyway. So if you're at a 7, it must come from a 0. Yeah. Okay, so we actually want to have... so we might want to just have a 2D array, like another 2D array that just starts at all -1s, or maybe like starts at all 0s, and then as we visit them, we like change them into 1s. So we could just do that, or like Boolean, doesn't matter. So yeah, at this 6, down is already visited, left works, up, right. So those two don't work. Down works, but it's already visited. Left works, and then down is already visited. Okay, so let's use that algorithm and trace it on this. No, I'm just kidding. We could trace it on this for like one of the 0's, because it gives us each 0. So if we have like 8, 9, 0, 1, 0, 1, 2, 3, 7, 8, 1, 2. Was it 1784? No, 1874. I wonder if this example is too large. Whatever, I got time. 8, 7, 4, 3, 0, 9, 6, 5, 9, 6, 5, 4, 9, 8, 7, 4. All right, let's just trace it on this part right here. That's good enough. Okay, so we'll start with this 0. So we go here, 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 here. Okay, so those are all visited. So if we trace back, 8 can't go anywhere, 7 can go somewhere, 8, 9. Okay, that works. This 8 can't go anywhere, 7 can't go anywhere, 6 can't go anywhere, 5 can't go anywhere. Okay, this 3 can go somewhere to 4, and then can't go anywhere. None of these can go anywhere, so we go back to the original 0. And then this one can't go anywhere. So obviously from here there is a path to 9, but we've already discovered this 9. 3, 4, 5, yeah. Okay, I think this looks good. So I really just want to have one function that I'm calling a lot, which I'll call search. So search takes in my position and the grid. I think that's it. Oh, and it should take visited as well. Okay, so what I'm thinking is, so my height is equal to grid. Okay, okay. So position is going to be a tuple, row, and column. So height is going to be grid of row, column. And then we're going to check each one. And we also need a bounded, which takes a grid and position. So this will just check if it's in bounds. So I'll say row, column is position. And then, so the violations to the rule would be if the row, I guess we could say like nm equals length of grid and length of grid of 0. So n is number of rows, which is the length of grid. Okay, this is right. So if row is less than 0, then that's obviously false. Or row is greater than n, that's or equal to n, because if it's like the length, we don't want to index at the length. Or column is less than 0, or column is greater than or equal to m. Okay, and then so this will be all the violations. So if any of the this will be true, so we want to return not. So basically, if any of these are violated, then this will be true, which means we want to say false. It's not bounded. So that sounds good. Okay, so we want to say if. So first check if it's bounded. Grid of row. So we'll do up, down, or sorry, up, right, down, left. Okay, so up is the row above you and the same column. So if that's bounded, and then also we should pass grid. Yeah, so that's actually the position. So we need to pass a tuple here. So row minus 1, column. So if that's bounded and grid of row minus 1, column equals height plus 1, then that means we want to search that one. So this condition means it's like exactly one elevation above, and this means it's bounded. So this means we want to search that one. So we'll search it. And we'll also pass. So I'm using row minus 1 and column a lot. I think it's okay. So, and then we'll pass position, which is row minus 1, column. And this should be a tuple here. Okay, and I also just want to check the problem quickly to make sure that it has to go up by exactly 1. So a path that starts at 0 and always increases exactly 1. Okay, perfect. I just wanted to make sure it wasn't like if it was a tie that you could count that or anything. So same thing for right. Okay, we also want to check if my height is 9. So if so this is a base case. So if we reach a 9, then we want to say visited. So I guess we should also probably have like a score count. So score. So when we reach a 9, we want score to go up by 1. And then visited of row column. So, oh wait, we want to do this for everything. So whenever we visit something, we want to set this. So we'll do a 2D array of booleans, which will all start out as false. So yeah, so it'll be true when we visit it. And we also want to check here that we haven't already visited it. So and let's do that here. So if it's bounded and we have not visited it, so and not visited row column, row -1. So this will return true or false. So if it's false, we have not visited it, then this is true, which is like the whole condition is true, which is good. Okay. All right, there we go. And we just want to do that for each. Maybe we can do this into a for loop. Where we say like, because this is a lot of code, so maybe we could just say like for I in range 4. Or like, you know, just repeat this code 4 times. Or no, we need. Oh yeah, wait, I have an idea. So for, I guess, x, y in a list of tuples, which will be above is 1, 0. To the right is 0 row difference, 1 column difference. And then down is -1 row difference and 0 column difference. And then to the left is 0 row difference and -1 column difference. Okay. So basically we'll just iterate through these, and then we can say if bounded grid row plus x column plus x and not visited row plus x column plus y. Yeah, this should be a y actually. And grid of row plus x column plus y. Maybe I call it RC. That's fine. Is equal to height plus 1. Then search with grid visited row plus x column plus y score. Yeah, so that looks better to me. Cool. So it's a list of tuples, and then so for instance in the first one, that searches up. So it'll check if row plus 1 column plus 0. Actually that's going to be down since I'm doing plus. So I'm going to just change that. So this is up now. This is to the right. Yeah, I think I just had those mixed up because up is above, right is the same row and +1 column. All right. Sweet. Not that the order really matters. I just thought it would be easier. All right, so let's read. Let's get the file inputs going here. Yeah, let's just actually do it on. Let's first start with the test input. That's always smart. All right. And I'm calling main, right? All right. And okay, so f equals open, and I would like to open 10 /hoofit dot in, in read mode, and then I'll print f.read, and I'll close f. So let's see if this works here. Oh, I read from this file instead of this file. So let's see if this changes it. Okay, perfect. So the way I want to organize this is obviously as a 2D array called grid. So we'll say grid equals line.strip for line in f.readlines. Print grid. So this will give me a list of strings, which I don't really want. So I actually want these to be a list. So that should work. All right, so now it's a 2D. And I also want to map them to integers, I think. Do I? Yeah, because height, I'm doing height plus 1. So I could just say grid. I could do it in this line, but that sounds kind of unreadable. Int x for x in grid. No, that's not gonna work. I could say map int 2x to x is a list, and then that we need to return it into a list. There's got to be a better way to do this, right? It doesn't work. Oh, I'm not printing it. This seems like really unreadable code, but it does work. I'll just leave it for now. Surely there's a better way to do that. that's heinous. No, that okay, let's just for line and f.readlines, we want to, and let's make grid empty. We want to map line, and this is a map object. Okay, I think this is fine. Yeah, that's probably better. Yes, we have to strip it. Okay, that's a little bit more readable. All right. Okay, so now we have grid. Visited, we want to we could do it in the same for loop. So we want to append to visited false times length of line. So 4 falses, 4 falses, 4 falses, 4 falses. Perfect. All right. Anything else? Oh yeah, and then we're also gonna have to. So this just solves one. So let's say I want to search. So if I want to search the position, so I'll just do it. So 0, 0. So I want to search 0, 0 with a score of 0. And let me just see what that gives me. There might be some errors. I haven't really checked it. All right, none. Well, I don't return anything. I guess we want to return score. Is this where we do it though? So I'm thinking how we want to keep track of score. Because if height equals 9, we don't want to search everything. So first of all, we don't want to search everything adjacent to 9. I don't think that'll change anything. So it'll search all 4 and then return score. So let me see what's going on here. I think this is not right. Okay, so we have grid. Position is 0, 0. Okay, so it's going to check above, which is not bounded. To the right should work. All right, now it's going to search position 0, 1. Yes, okay. And now it's going to check above, which is not bounded. Now it's going to check to the right, which should work. Okay, so it should go to 0, 3. Okay, so if we look at the example again, we're here. So now it should go to 4. So actually it would be 1, 3. Okay, so it's still at 0, 3. 1, 3. Oh, it did up and right or false. Okay, so it should do up and right or false for 1, 3 as well. 2, 3. So if we look at our graph here, of visited, this doesn't look right. True, 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 false. So that's not what we want, obviously. Okay, so I'll just keep going. So we're at 2, 3. Now we're at 3, 3, which is the bottom left corner, or bottom right corner, 6. Now it should go to 3, 2. And now 3, 1. I'm just doing this because I want to see what happens when we get to score. Okay, so now it should go to 3, 0. So, nope, nope. Okay, so this should work. It should search. 3, 0. So now we're back to, so what's score? 0? All right. So I didn't have a marker here, so I couldn't see what happened. Score plus equals 1, and then it returns. Okay, so this thing is only... It's just like doing it in local and not returning it anywhere. So maybe I could return this at every... So this will return score. Yeah, so tracking... Because here I don't really want to make a function call. Maybe I should check here, like if... Well, I don't really... I mean, maybe what I could say is if so if your height is 8 and you found and you're in here, that means you found something adjacent. So what I could say is like found equals 1, else found equals 0, and do like plus found or something like that. So that means we found a 9. And then, yeah, if height equals 9, we just want to return. And then so that way we'll increment score by 1. Okay, still 0. I also just want to print visited again and see if that's... Okay, so there's 5, which is not what we want. So let me print length of line here. 5554. So let me print line and see what it is at each time. Does it have the new line characters? Oh, line.strip. Could that be it? Okay, that works somehow. Okay, so that fixed that. It doesn't seem to be working. I'm at 42 minutes here. All right, so let's simplify what's going on. So it seems to be traversing properly. It just seems like the score is not working. So this probably comes down to like a lack of understanding of recursion for me, which is good. It's good that I'm doing this then. So it does seem to be getting to 9. So let's see what happens. Why are we... Okay, so just going to skip through this a bunch until we get to... We're approaching 9. 3, 1, there we go. Okay, so height is 8. So let's see what happens here. Okay, that did not... Okay, so this is checking to the right. This is checking to the left. Okay, so height is 8. So found is 1. And now it's going to pass... Okay, search the 9. Yeah, I see why this is... Yeah. So now it's going to go to 9. And now height is 9. And score is 1. And then do we just return score? So here if we return score, or maybe we want to return 1, and because it kind of reminds me of folding in a way, like... So 9 we just get out. Maybe we should return 1. And then here we can do... Because when we return this, we do basically nothing. So this was what called it, and then it returns 1, and we do nothing with that. And score is just permanently 0 for some reason. And this didn't seem to work either with the found. Right? Because when you get to the 9, that's when it sets score to 1, but you don't do anything with that. I mean, I could just have like a just like an array, and every time it's a 9. I mean, all right, I could do this. I'm upset why I don't understand why that's not working, but I could say 9s dot append position, and then at the end we'll just return like the position. We'll return the length of 9s, I guess. So instead of passing 0, we'll pass an empty list. Okay. So that worked for this one. Let me try a different test input because I'm not feeling extremely confident. Oh, I also forgot about dots. So I think what I'll just do is to my bounded function, or grid of row column equals dot. Then, you know, that also just won't include dots. Okay. So I wanted to do that. And I don't know what that is. And now I want to try it. And now this starting position is row 0, column 3. Invalid int. Oh yeah. We can't map. Yeah. I could just say int x for x, int x if x does not equal period, else x, whoops, else x for x in line.strip. Like that. So let me just print grid and make sure that works. So grid is dot dot 0. All right, this seems to be working. Obviously the answer is not. So let me print grid at 0, 3 and make sure. Yeah, it's a 0. All right, back to the debugger. So when it hits down, it should. So this is down, so it should work. It does not. So for some reason it's not detecting. Could it be bounded? Grid equals a dot. Grid, oh, what? I forgot that. 2. Alright, so that seems to be working. Okay, so it worked with those two. Let me try this one. And then just see if I can find any bugs. Okay. So 0, 2 should be 5. Why is it a 1 though? Oh, okay. 0, 2 should be 5. 0, 4 should be 6. So basically this is the position of the trailhead. So I'm just doing that. 6. Row 2, column 1, 2, 3, 4, 2, 4 should be 5. Okay, and then I'll just try this one here. Row 0, 1, 2, 3, 4, 5, 6. So 6, 0. And if this works, then I'll just implement the rest of the code. 6, 0 is 5. Okay. Okay, so it looks like this is working. Okay, so now this part. Okay, so we want to know all the Trailblazer locations. Or like start positions. Why am I saying Trailblazer? Trailhead. Trailheads. Yeah, I think I want to say here 4x, I guess like 4 points in line.strip. If points equals 0, then I want to say trailheads. I need the position of it. Alright. I could do that with indices and everything. I'm just gonna say find all trailheads of grid. So this will just take in a grid. It's just going to loop through it, and if it's a 0, if grid of ij equals 0, then trailheads dot append grid of ij. So this, I'm almost at an hour, so I don't want to take too long. So let me just see if that works. I actually don't want to append. This would just be zeros. I want to append a tuple of the position of the 0.